deadline to sign up for college credit. Blah, blah, blah. Mr. Green, I need the thing for my free and reduced lunch. Go talk to Miss Peterson. Mr. Green, I need to pay. Blah, blah, blah. Go talk to Miss Peterson. Hey, shut up. Thanks. Mr. Green, I can't get the thing to sign up. Well, you're all big kids now, so I gave you the form, so you could probably figure it out. Email so-and-so, call whatever, da-da-da. I can help out a little bit, but it's pretty self-explanatory, okay? We'll make it happen. Let's just get her done, okay? So, Friday, the last day for that business. Today, tomorrow, you people have a quiz. Okay, but today we're talking about section 1.5. It's inverse functions. So what do we know about inverse functions, Connor? I'm just going to start back there and kind of work around. Nope, wrong. What do we know about them? Well, what's the opposite of multiplication? So they undo each other. Okay? So, back in the day, you remember, 2 times 3 is 6. And then later on they went 6 divided by 2, and you went, I don't know! Well, that's ridiculous. It's absolutely ridiculous. So what do we know? We know that when we have a function like y equals 2x or something, right? You've got a domain, and you've got a range, and that's lovely. And in the case of these guys, it's all reals, right? There's nothing you can't times by 2, and there's nothing that when you're going to get every answer out. Coming out the other side. It's all real. So it's easy. But wait. Mr. Green might feel like that the opposite of multiplication is, well, I feel like it's division. So I feel like it's this function right here would undo it, yes? Except these x's are really the what's in this equation up here. Feel like they're the y's, and I feel like these x's are going to be the y's down here. Remember? Because inverse functions, our domains and our ranges flip-flop, yes? On inverse functions. Yes? Remember this? Yes? Yes, Mr. Groom. I know, right? Oh. Nice. So in the case of this one, you're like, geez, it was all reals. It's still going to be all reals. That's right. That's right. That's right. So up here on this first one, when you put in a 3, you got out a 6, yes?
Yes.
Down here, when you put in a 6, you're going to get out a 3, yes? It's going to undo it. Nice. Question for you, Ms. Morse. Suppose you get, I don't know, some manure on your hands while you're cleaning your horse stall. Can you fix that? Yes you can. Suppose you I don't know, you scoop up too much peanut butter when you're making a sandwich. Can you undo that? Yes. Suppose you accidentally cut your finger off with a skill saw. Can you fix that? Yes! Yes, you can. Suppose you accidentally run your finger through a meat grinder. Can you undo that? No. So there are some things in life that we can undo. Yes? And there are some things that we can't undo. For instance, when we see this later on, here's one of my favorite functions of all time. I call it the buffet function. It's a constant function. It's $10. But Mr. Green, what if I go through the line 20 times? It's $10. But what if I go through 7 times? It's $10. Mr. Green, what if your grandma goes and she eats like a half a plate? It's $10. But I will go through more because I feel like I need to get her money's worth too, because that's what I did when I was a kid. Grandma ate a half a plate. I better eat more. Okay? I don't know why. It's not like I paid for it, but I always feel like I should make up for it, right? Which I did. Now, here's my question. Suppose you put in a 6, right? What comes out? 10. And a 2? And a -1? And a 0? Yeah, there. A whole bunch. Don't screw with me. A whole bunch of them. So if I ask you, oh, Betsy, where did 10 come from? If you were the calculator, this is you, you're a calculator, and I put in 10 or whatever and tried to undo it, the calculator would go, huh? Huh? It couldn't do it because why? Mr. Grimm, how many are there? Every one of them is matched up with 10, yes? So which one did it come from? Oh. And so what you may recall is last year we talked to you, I didn't, but Mr. Patterson did. We talked about not only the vertical line test, which tells us what? If it's a function, what if it passes the horizontal line test?
It has an inverse?
That's right. So it has an inverse that is a function. So horizontal line test tells if the function's inverse is a function. Very nice. So here's basically the deal. If it passes the vertical line test and the horizontal line test, we say that it is a one-to-one function. That is, each x has one y, and each y has one x. Monogamy, if you will. And that's swell. Therefore, when you ask the calculator, hey, where'd the 2 come from? It'll go, oh, it came from 7. Oh, okay, that's nice. Because there is an actual rule that it can follow to get back to it. See? Again, I like pictures. So, here's a meat grinder. The grinder, I'd say it's an old school one like this. By the way, if you're so dumb you run your hand through a hand crank meat grinder, you probably want to get a new job. But look, steak. What comes out? Hamburger. Oh, look, a roast. Hamburger. Okay? Your finger. Hamburger. Where did it come from? I don't know. Can you undo it? No. Can we stuff the hamburger back up and get steak out of it? No. No. Not possible. I've always liked that picture because I've seen people cut their fingers off with a skill saw or whatever, and then they get sewed back on and they kind of work, but you look like Frankenstein. It's weird, but it does go back on. It's just odd. But if you grind it off, not so much. Okay? Now, the question then becomes, well, how do I do this? So if you have functions like this, I don't know. Watch Mr. Groom draw a function. Does this one pass the vertical line? Well, yes, it's a function. Does it pass the horizontal line test? I don't know. Maybe. Sure looks like it might. Right? So will it have an inverse? Sure. Yeah. What will its inverse look like? If this is f of x, if I were to sketch it, what would its inverse look like? Well, here is the line y equals x, yes? And what do we know about inverse functions in the line y equals x? They are reflected across it, yes? So if you think about this, these up here are negative x's and positive y's, yes? When they flip-flop, I'm going to get positive x's and negative y's, yes? So stuff that's in quadrant 2 will come down here to 4, and vice versa. Stuff that's in quadrant 1 will stay in quadrant 1, though, yes? Because positives are not changing. Down here, they're negatives and negatives. So what's in quadrant 3 will also stay in quadrant 3. So what I'm going to see is I'm going to see a what do I call this thing I'm drawing? A reflection, yes? This red line is the inverse of that function. So look at this point right here. This point right here, it's like 4, 4. Dude, it's like 4, 4. And then when you flip it around, what do you get? Well, it's like 4, 4. So I didn't change. What? And then like 1, 5, 1, 5, whatever. Oh, that's probably not 1, 5. That's not 1, 5. 1, 1, 3. That'll work. 1, 3.
Thank you.
Will get switched to become what? Like 3, 1, right? And so forth and whatnot, and so forth.
So is the inverse written as f negative x or?
Excellent question, star student. That is correct. F inverse. Nice. Nice. What? What? What did you say? I can't hear you. What did you say? What'd you say?
I said that's what it was, and Ben told me I'm wrong.
Oh, don't listen to Ben. What does he know? Listen. If f of g is equal to g of f, and they both are equal to x. In other words, they both undo each other. Then what do we say? Then f and g are inverses. Notice it has to work both ways. Oops, f and g. There's a d in there somewhere. Okay. Do you need a calculator? Nice. Nice. Hey, here's a function. F of x equals sine of x. G of x equals inverse sine of x. Mr. Grimm, they totally have to be inverses of each other. Right? Right? They have to be. Right? Well, hang on to your horses. Okay? If I said to you that the sine of the inverse sine of x, what would you expect it to be? Would you expect it to be x? Is that a question? Well, it feels like it should be. It feels like it should be. But then the sine of the inverse sine, oops, I did it wrong. The inverse sine of the sine, there we go. So the question is, do they both get you back where you started from? Brooke, would you pick me an angle, Brooke? One of our friend angles, one of our lovely friend angles, you know, like pi over 4, or pi over 3, or 60 degrees, or 30 degrees, or
45 degrees.
45 degrees, she says. Good for you. Good for you. Now that you've said that, what is the sine of 45 degrees, Brooke?
Is it bad that I don't have it memorized yet?
So it's not good. It's not good.
Can I look at my notes?
It's not good. But there it is. Square root of 2 over 2.
Okay.
So if I asked Betsy, oh, Betsy, my calculator. Oh, great and glorious Betsy. What angle, Betsy, this is what this is saying to me, what angle has a sine of square root of 2 over 2? What's Betsy going to say? 45. And then I say, oh, Betsy, what's the sine of 45? It's going to spit out square root of 2 over 2, yes? In other words, I'm going to get right back where I started from. I put in the square root of 2 over 2, I got square root of 2 over 2 back out. Boom, boom. Yes. Now, what if I said to you, oh, great and glorious Betsy, what is the sine of 45? Betsy will say what? Square root of 2 over 2. Oh, Betsy, what is the inverse sine of square root of 2 over 2? She will say 45. In other words, I put in 45, I got out 45. Yay, it looks good. It looks promising. But Angel, what if I picked a number that I didn't know anything about, like, say, well, 300 degrees. Now I know what 300 degrees is. 300 degrees is 5 pi over 6, yes? Yes? Okay. And if I said to Betsy, oh, Betsy, the sine of 300 is negative square root of 3 over... No, that's not true. It's a pi over 6 angle, stupid. No, it's pi over 3. Yeah, I was right the first time. Square root of 3 over 2. Square root of 3 over 2. So if I said to her, oh, Betsy, do this, please, Betsy will do the following. She will look at this, and she will go, oh, I know what this angle is. This angle is negative 60 degrees. That's what she'll say. Take your calculators out. If you have a calculator, take it out. But Mr. Grimm, I only have my cell phone. Then use your cell phone. Everybody, get a calculator. Get yourself in degrees. If you don't know how to get in degrees, it's by God, it's high time you learn how to do that. Oh, in the video last night, it's pretty funny. I'm starting up the stupid calculator. And like it didn't start right away, so I tried it again. And then I had like 3 calculators going at the same time. It was bizarre. All right. So I'm in degrees right now. So I'm going to say, oh, Betsy. So inverse sine. And then I'm going to do the negative, the square root of 3 divided by 2. And Betsy says negative 60 degrees. Yay. Now, let's take the sine of that. So the sine of negative 60 is, it's that thing right there, which is the square root of 3 over 2. It's the same answer. So going this route, we end up with exactly the same answer. Because this is approximately negative 0.86666 or thereabouts, okay? Like, whoa, that's cool. I started with x, I finished with x. Not so fast. Not so fast. Suppose I said to Betsy, what is the sine of 300 degrees? What would Betsy say? So I'd say sine 300, and it spits out this negative square root of 3 over 2 business, yes? Which doesn't really surprise me a great deal. Now I ask her, hey, what is the inverse sine of that? You're expecting what angle? You're expecting 300, but you're wrong. Oops, that's cosine. That would really be wrong. Oops, enter, parentheses. Oh, it's negative 60. It's negative 60. Wait a minute. I put in 300 and I got out negative 60? What? Did I get back to where I started from? No. And here's the deal. This is kind of the long and the short of why we study these today. There are quite a few functions that are inverse of each other we mess with on a daily basis. And we wave our hands at them sometimes, and we kind of go, oh, that's right. Patterson said you're going to get an angle in negative 60, so you have to fiddle fart around and figure out if it's supposed to be positive 300 or whatever, and you got to fiddle fart around about it. That's right. It's not wrong. But today we're going to get into a little more of the why, for, and the how comes. Okay? So you've done this before. It's not like it's brand spanking new. We are not going to do a lot of this. Mr. Room, I have 3x plus 2. Can I find the inverse? Yes. Yes, you can. X minus 2 over 3. This is y, or if you prefer, f inverse. Okay, that's how you do it. Okay, on a nice linear function. But we're not going to do a whole whale of a lot of that. Okay, we're going to get a lot more into functions that we know and love dearly, we use all the time, and take a look at how they act and respond with one another. So, for instance, our good friend y equals e to the x. That'll do it. You literally said make sure you're in degrees. Now, you could have done it in radians, it just wouldn't, it'll look different compared to what we were doing. Okay, but same thing. All right, yes? Oh, just go to the right, it's fine. So e to the x looks like this feller, whoosh, like so, yes? Crosses through here at 0, 1, obviously, right? If I were to sketch that, his inverse, it would look like this. Look like what? Like that, ish. And where does it cross right here?
1, 0.
Better be 1, 0. Hey, look, it never, if I'm looking up here, x is all reals, right? What's the y up here? The y is bigger than 0, yes? So down here, this function, whatever it is, x better be bigger than 0, and y better be all reals, because they switch each other. What is this function down here? Natural log. Very nice. The natural log is the inverse of e, yes? And again, where it comes from, we use both those functions a lot, so you need to be comfortable with them. Notice how this one is always increasing, yes? Always increasing? It's always going up? Is this one always increasing? It is always increasing. How do I know that? Because it started way down here, and the y's are all reals. How's it going to get to all reals if it doesn't keep going up? It's got to. Right? Who goes up faster? Well, this one goes up faster, obviously, right? For instance, this one here might be something like 2, or not 2, like 120, like several billion or something. Several billion. Because e to the 120 is a fairly large number, I think you'll agree. Out here somewhere, there's going to be several billion, 120. Right? By several, I might mean several 100,000 billions. I don't really know. It's a lot. It's a pretty healthy number. Okay? Ish. Okay? Now, again, Kind of a big deal. Natural logs, e to the x, they undo each other. That's kind of handy because what if you had e to the ln of x? What does it come out to be? X. What if you have the ln of e to the x? Oh, it's x. Ta-da. Well, that's not weird. You all got done at the exact same time.
That's exactly what I was thinking because I'm also done, but everyone just stood up.
Yeah, you can't have that.
Well, I kind of sat there for a second. Yeah, I think
All right. Anyway, I don't care. There it is. Okay? They undo each other. All right? Why is it, Ms. Morse, if I ask you what is the ln of negative 2, what does your calculator say? Well, ask it. Oh, for God's sakes, really? 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 Okay, listen, sister. That's why we're talking about this. Right here, look at it. The x's better be what? Straight up positive. Yes? So if I ask you what is the ln of negative 2, you should go, what are you talking about? If you ask Betsy, what should she ask you? The same thing. Go ahead, ask her. Betsy, the calculator. Ask her. Ask her. You literally type it in like this. I was just kidding with you, dear. It's okay. I just want to see you do it. ln. I just want to see what would happen. Now the nice thing about the 89, it tells you straight up it's a domain error. That doesn't true on the 84 or something. They'll just go, right? What does that little calculator say there, Lacey? Just for fun. Oh, it actually says domain error. That's weird. And that's cool. Yeah, but whatever. Personally, someday I would like to wire a calculator, put a little speaker in there that like tells you you're an idiot when you try that. I think that'd be hilarious. You worthless idiot. Pull your head out of your butt or something. That'd be hilarious. Now, anyway, what other ones have we seen? Well, we just saw inverse sine a minute ago. Here's sine of x. What is wrong with sine of x? Well, wrong with it. I feel like it's not 1-to-1, is it? It doesn't pass the horizontal line test, does it? That's a problem. That's a problem. But the sine function, is there anything new ever on the sine function? I feel like it's the same thing over and over and over and over again. Kind of like, okay, this is how I felt about last year. Great. Here we go again. Here we go again. That's why last year I'm still not in a great humor this year, but a little better than last year. But literally, last year I put these signs up. There's one outside. There's nothing new under the sun. Here we go again. And again. And every year it was just kind of, every day I felt like last year, what kind of new crap are we going to see today? Because it's the same stuff we've seen before. It's just repackaged, sort of, but it's the same stuff. Okay. So when I see this thing, the sign just repeats. So what we're going to do is, if I asked you where would you cut it, I think most of us would go, you know what, Mr. Groom? I think we'd cut it so 0 was in the middle of it, right? Or in there somewhere. And we'd go to the highest point, and we'd go to the negative point, like so. And I feel like that my domain here, this is y equals sine x, sort of, between negative pi over 2 and positive pi over 2. And what is the domain of that? Where's my domain back and forth between? What's the smallest y value? -1 and +1, yes? Nice. So I ask you, what would inverse sine have to look like then? Well, we'd reflect it over y equals x, yes? So instead of being curved over like this, it's probably going to be curved up like so, yes? Instead of being curved over like so, it's probably going to be curved like this, yes? And what happens? So inverse sine of x is going to look like this. What are its x values going to be? Is x's are going to be between where and where? -1 and 1. And its y's will be between, or if you prefer, right? Which is why when you ask Betsy, oh Betsy, I'm going to give you a number like negative square root of 3 over 2. Betsy will find the angle that has that right down here, you see. has that sine function, and it'll throw back out to you negative 60. Now think about that for a minute. Here's my unit circle. Here's 300 degrees right here. Right? Right here, that's the sine of 300, is that length downwards like so. But 300 is another way of saying negative 60. They get to the same location, yes? So the sine function, the inverse sine function, is only defined from here to here. Okay? So if you ask Betsy what angle has this negative sign, it's going to give you an angle in quadrant 4. If it has a positive sign, it'll give you the one in quadrant 1. And then you have to, apply it accordingly. Now, this thing keeps going forever, right? I mean, the sine function does. Well, think about this. How many times does it have this same negative? How many times does it have this same negative sign amount? In round figures, a lot of times. It's going to keep doing it forever. So you have to be able to match it up, right? Every 2 pi, it's going to hit that baby again and again and again and again and again. So you have to be smart to figure that out. Right, Lily? Right. Now, Mr. Grimm, let's talk about cosine, Mr. Grimm. Thank you. I will, Lily. That's swell. So cosine looks like this deal, yes? No, sort of. And like this deal, sort of, yes? Using the same thought process as last time, that is, I'd kind of like to have 0 in my answer, somewhere in my answer. Where would you cut this thing? Where would you cut it? Here's 0, here's like pi over 2 right here, here's like pi right here, here's like negative pi over 2, here's negative pi. Where would you cut this thing? Because I would want it to be 1 to 1. Whoa, 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 whoa. If I cut it here and here, does it pass the horizontal line test? No. Where else would you cut it? I want 0 in it, Fosha. 0, and pi. If you cut it between there and there, will you have the highest and the lowest points? And everything in between? Yes. Is it 1 to 1 in that region? So this is y equal cosine x. Oh, good. I know Levi didn't cheese the last one I turned in. That's good. Now I know, right? So 0 pi. And of course, this to this, right? Oops. Yes, right. Almost freaked myself out. Yeah, there it is. Yes? Es muy bueno? Sí. All right. So, this one is really hard for me to draw. I suck at drawing. I am really bad at it. So allow me to get a pen and let's sketch in the line y equal x, okay? There's y equals x. I sketched it in. Good for me. Yes? Yes? Now, what about these guys up here? What are they going to do? Well, this point here, which is 0, or no, it's not either. It's pi over 2 comma 0. Yes? Where is he going to be? He'll be up here somewhere, yes? Right? At 0 pi over 2? And this point here, which is 0, 1, is going to be where? 1, 0. Right? And these points down here that, for instance, at pi comma negative 1, where is he going to show up at? Negative 1 pi, right? So it's going to look something like this. And again, I suck at drawing, so pardon me. Right? Somewhere up in there, yes? I suck at it, I'm sorry. I'm terrible at it. I'm terrible.
Oh, you're not helping, Ben.
I don't want to hear anything out of you, pal. Nothing out of you. Now, I like my Desmos.com. Makes me very happy. I think it's very nice for demonstrating crap. So in the old Desmos.com, with the old function, sine, x, you can do this. You can go, let's see, squiggly brackets, if I can find them. Squiggly brackets. And then I can go like negative pi divided by 2. Less than x less than pi divided by 2. There's my function that I have chopped, truncated, if you will. And then I can also go, hey, let's look at inverse sine, Mr. Grimm. Q, arc sine x. Bam. Hot dang. Basically what I drew. What do you know about that? Nice. Can I do the same thing with cosine? Well, of course you can. Of course, that's not the right restriction, is it? No. So you want to go from 0 to pi. Oops, that's a 0. It's literally a 0. I mean, it's supposed to be a 0. It's an O. Thank you. I know. Yes. Okay. And then a little arc sine action, arc cosine action. That'll work. Sure, whatever. There they are. Not too bad. Not too bad. What?
So what you see in the textbooks where the swoosh there is repeating over and over, what's that?
What now?
So if you had the graph and you had the y equals sine x, you see that repeat a lot in terms of the line. Is that just showing?
There's cosine. It goes on forever and ever 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 and ever. If you ask the calculator, where does that thing equal 1? Well, let's say equal a half. Let me draw this on there. If I said to my calculator, what angle has a sine of a half? Is it this one? Yes. Is it this one? Yes. Is it that one? Yes. How many of them are there? An infinite number of them. So that's what a calculator can't tell you. It'd be like, I don't know. Which one are you talking about? So it restricts it down to just this portion of the graph. And says, so on this portion of the graph, I can match it up with one spot that has that's true for. Okay, watch this. Matter of fact, I can do this. Let me put this back on. It's right there. It's literally right there at, let me zoom in just a skosh. Ah, crap. I don't do that. Don't do that. Ah. There you go. Okay, let me exact. Always forget I have to do this kind. Literally right there, that's where it's equal to. You see this? Pi over 3? Okay. But watch me come up here to pi. Watch me come up here to a half. Okay. If I come up to this equation right here, this is the arc cosine. And when I get to a half, what does it come? What does it say? Pi over 3. So that blue line will tell you to match that up with it. Okay. It'll match it up to pi over 3. But Mr. Grimm, it's not really pi over 3. It happens to be in the, you know, it's like gone around another 2 pi times. That's fine. Then you have to be smart to figure that out. Okay? The calculator can only give you one answer. That's why functions are important. Okay? Only one way to do it. Shh. Thanks. I see no one's going to sit outside today. That's fine. That's weird. Yeah. No. So y equals tangent x. This is another one we see frequently. What does tangent look like? It's got asymptotes at pi over 2, yes? And negative pi over 2. And it does this business, and then it does it again, and so forth and whatnot. Where would you cut this one?
It's already cut for you.
I feel like it's already cut for me. That's right, exactly. And so tangent is going to be, we're going to do it between negative pi over 2 and pi over 2. Ooh. Is anything wrong with the way I put that on there? Yes? It can't be pi over 2. Well done. So technically it's that. Watching the video? Okay. Okay. Whatever.
I did something really stupid on the quiz, but I got the right answer.
Question.
So
if we integrated weird, but on the second one we
on the third one.
third one, I guess.
So let's say we did it wrong in the first one, and then we plugged it in on the third one, thinking last one, would that be counted against us?
I don't know, maybe a little bit. Now, obviously y here is all reals, yes? Oops, I don't even know what I'm trying to write. All reals, right? Because it goes up forever and all the way down forever? Now, draw the inverse for me here. Well, it's going to look something like this and like this. Yes? So it feels like to me anyway. So inverse tangent is going to be defined to be between where and where? Well, its x's are going to be what? All reals. And its y's are going to be between negative pi over 2. In other words, an asymptote. And one up here as well. Oh, by the way, the over-under bet for back to school night, how many parents show up? 3. For me. The over-under bet. All right, so I'm just telling you right now. I checked in Vegas this morning, Mr. Groom's class. Total number of parents to show up. The over-under, if you're going to bet on it, is 3. Okay. Yeah. So I will sit here for 2 hours and 3 parents will come. Let's see. Probably your mom. Brandon's parents will show up. And some other random kid will show up, parents.
I can send my parents if you want.
It's no big deal. I don't care. I literally don't care. It's just funny. I sit here, twiddle my thumbs. Oh, hi, I'm so-and-so's parents. I just hope this year I can pull off the, your kid is who now? Because I have a really hard time with these. The last few years, names are just not sticking like they used to. So it's bad. I especially love when a parent comes in, totally different last name than their kid. That does not help. That does not help at all. I'm so-and-so. I'm random kid, random boring kid's name. Like just boring name kids. Like Joe or something. You're like, can you be more specific as to which one? And then they say the last name. I'm like, crap, that's still not helpful. Okay. Yeah. Anyway, let's see what else we got here. So, what other kind of functions have we seen, people? Sines, cosines, inverse cosine. Shh. Can we do arc secants and stuff like that? Well, of course you could. Do that yourself. Well, okay, I'll do one. Why not? I will do. You tell me. Is this? Well, let's do this. Let's do secant. What would secant even look like? What would secant of x even look like? Well, it's 1 over cosine, right? So let's start with cosine. Well, 1 over that, right? So 1 over 1 is, well, it's 1, yes? Uh-oh. What is 1 over 0? Ah! Asymptote. 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 Right? Hey, 1 over positive numbers but are small are going to be headed where? Up. Up. And 1 over negative numbers are going to be headed down. And then it's going to repeat itself, yes? Where would you chop this fella so that you got all the information, didn't lose anything? Where would you chop it? Well, let's get rid of this cosine. We don't need him anymore. I personally would chop it here and take this piece, right? And here, and take this piece here. Do I have every value at that point? Yeah. So think about this now. So I'm saying y equals secant x. I'm going to pinch it between 0 and pi, where x, of course, cannot equal pi over 2, yes? That's a problem at pi over 2. Right? And my range is what? Be careful. Is it all reals? No. It's not all reals, is it? Because can it be 0? No. It can't be 0. So it's got to be, check it out. I could write it like this. Greater than or equal to 1 or less than or equal to negative 1. But the big kids would say, let's let the absolute value be bigger than or equal to 1. Okay, that's what the big kids would say. Okay? And so what I end up with is this thing. Ah! What would the inverse of this beast look like? Let's draw it. Scream, I need some help. I feel like this is pi comma negative 1. You're welcome. And I feel like this is pi over 2. That's a line, pi over 2. Currently it's x equals, yes? In a minute I think it's going to become y equals, I think, yes? And this is the point 0, 1, right? So where will they all show up when I reflect them? Well, 1, 0. Here's the line y equals pi over 2. No, it's pi, negative pi, oops. So it's going to be negative 1 rather, negative 1, and then up here at pi somewhere, yes? Right. Yes? I think so. So it's going to be coming down like so, I believe. if I'm not mistaken. And where else are we going here? Oh, yeah. And then we're at 1, 0, and we are going to be approaching the same line, but more like this, yes? Yay! And if you are any kind of artsy-fartsy, if I can pull it off, you can pull that off, okay? Nice. So this red line would be y equals arc secant, or inverse secant. Okay? Where is it defined? Well, its x values will be what? Greater than or equal to 1, absolute value.
Yes.
And its y values will be between 0 and pi, right? But it better not ever equal pi over 2. Boy, I haven't graphed that in a long time. Let's go ask Betsy. Oh, great and glorious Betsy. I have a question for you. Arc secant. That's pretty cool, huh? Oops, that's the wrong direction, stupid. There you go. Boom. Boom. Hey, let's graph the line y equal pi divided by 2. Oh, look at that. It's a freaking horizontal asymptote, yes? Nice. And away we go. Oh, look at this point right here. Check it out. This point, negative 1 pi. This point, 1, 0. Good stuff. Okay? So arcs are inverse functions. Pretty big deal. Pretty big deal. Let's see what else they talked about. And there's one more thing I think I wanted to mention that I forgot about. And then you guys can have some time to work because we are basically finished at that point. Suppose I asked you, what is the inverse sine, no, the sine of the inverse cosine of 3/4? Mr. Graham, 3/4. I didn't really study my stuff and my little chart you gave me, but I don't remember 3/4 being one of them. That's because it's not. But think about this for a minute. I could draw a picture. Not just any picture, a right triangle. So there is some angle theta here. I don't know where it is. Maybe it's here, maybe it's this one, but it doesn't matter which one you want to use. Just be consistent with yourself. Cosine is adjacent over hypotenuse, yes? Meaning the opposite side must be square root of 7. Yes? Yes. And so, if I say to you, this thing right here, that's this angle. Okay? It is this angle right here. But what is the sine of this angle? Well, it's the square root of 7 over 4. True. True. Now, you want to do another one. I totally understand. Suppose I tell you this time that your angle is in the third quadrant. Quadrant 3. And suppose I say to you that the angle like so. So if I tell you going into this problem that your angle is in quadrant 3, what do? Well, this thing wants me to draw a picture. Oops, that's weird. I mean, it would totally work. It's just weird. And this angle right here is my angle. That's great. And it says the sine. Well, that's opposite over hypotenuse. So that makes this the square root of 8, I think. Is that right? Check my math. That seem reasonable? 9 minus 1 is 8. Yes, that's good. So then, Mr. Groom, I want to know what is the cosine of this angle? What is the cosine of this angle? What? It's square root of 8 over 3. Positive or negative? Quadrant 3. So we're in quadrant 3. So where will that put us? Quadrant 3 is going to put us over in this quadrant, yes? So the cosine will be negative. Okay, so just be aware of that. Just know that going in. Okay. Now, let's do one that we know the answer to. What is the cosine inverse cosine of the sine of 2 pi over 3. I like this one. 2 pi over 3, pi over 3. What kind of angle are we talking about? Pi over 3. What angle measurement is that in degrees? Probably will be on the test tomorrow, by the way, quiz tomorrow. 60, because we know pi is 180, yes? So we're saying pi divided by 6, pi divided by 3 is 60, times 2 is 120, yes? So in your mind, one should be looking at this thing in your head, going 120, well that's over here, Mr. Groom. That's really just a 60-degree angle over here in this quadrant, right? So the sine there is going to be, this is going to be the square root of 3 over 2, yes? Now, what angle, this is what this is asking me, what angle has a cosine of the square root of 3 over 2? What angle has a cosine of square root of 3 over 2? What is that, Garth? 30 degrees. I'm just going to go with pi over 6 if that's cool with you. If that's okay with you. I'm going to do that. Yeah. That's what I'm going to do with it. Okay? So this angle in here is one that we know. We know the angle of, we know the sine of it is pi square root of 3 over 2. And then we want to know what angle has a cosine of this cosine. Well, it's pi over 6. Not very hard to do. Just see if you're paying attention. Okay, they're functions in a function. Where do I start? Inside, like always. Okay. This wants to know what is the ratio of this angle. That is the ratio of the opposite over the hypotenuse. It's this ratio. All right. What angle has this cosine ratio? It's this one. Okay. Notice it's which one. Stream, aren't there an infinite number of them? Not where inverse cosine is concerned. Inverse cosine has one answer. Okay. You're going to see something like that. It's going to be a good time. You'll also see one like this fella. Ooh, see if you're paying attention. Stream, I want to know the tangent of the arc secant of -2. Well, that's disturbing. Now, this is one that we should know. What is secant? Cosine, right? It's 1 over cosine. So secant is 1 over cosine, right? So if this is -2, this should be then 1 over -1/2, yes? So another way to write this would be the tangent of the inverse cosine of -1/2. What angle has a cosine of -1/2? Are my videos not good enough? No. Now, what angle has a cosine of 1/2? What angle has a cosine of 1/2? It's pi over 3. Shh, but wait, stop. It's not just any pi over 3, it's negative. So it's going to be a 60-degree angle in quadrant 2, so it should be 2 pi over 3. Okay, and then I want the tangent of that fella. So the tangent of that guy is square root of 3. Square root of 3. Negative square root of 3. Now, tomorrow, on your quiz, up through section 1.4 on the quiz tomorrow. Look for about 5 or 6 questions. You do not have the whole period to work on it. You cannot diddle fart the whole period on 5 or 6 questions. So about 25 minutes or so, tops. All right, have a nice day.